All right, let's talk about second order reaction. So if the reaction is second order, you can do math very much like I showed for the first order and convert that first order rate law to the first order integrated rate law. And you can convert the second order rate law to an integrated second order rate law, which I'm showing here. And I won't bore you with the calculus because this isn't a calculus based course, but 1 over concentration of the reactant A at time t equals positive AKT plus 1 over A at time 0, where A is the stoichiometric coefficient, K is the rate constant, T is the time. Notice the slope is positive here where it is negative for the first order rate law. And notice it's 1 over the concentration instead of natural log of the concentration. If we plot natural log of the concentration, it's not going to be linear. And if we scroll down, you can see natural log of the concentration versus time. You see there's a little bowing there, and so that's not going to work. But you can see 1 over the concentration is a straight line, so we can tell that is a second order reaction. So if we look at this reaction, we got two NOCLs reacting to form 2NO plus Cl2 gas, rate constant equal to 0.020 liters per mole per second. If the initial concentration is 0.050 molar, what would be the concentration after 30 minutes? All right, there's a couple of things to consider. One, the coefficient is a 2, unlike my example in the first order where there wasn't a coefficient to worry about, so that A is going to be meaningful. 2, the units on the rate constant is seconds, but the time you're given is minutes, and you can't mix and match your units, so we're going to have to fix that. So going to the paper, you can see I've copied everything down. So we got 1 over A at times E, AKT plus 1 over A at times 0, and then I've just substituted in the reactant for our particular question. As we mentioned, the coefficient's 2, so A is 2, and then I've just copied all the material from there. But that 30 minutes we're going to have to fix. Remember, there's 60 seconds in a minute, so we're going to have to end up multiplying that by 60, and that's going to give us 1800 seconds. And then that'll fix it so our units match. But I still am going to need how much is left, so I don't really have to solve for anything. But remember, I'm talking about 1 over, and it's easier to solve for that once I've got an answer. So I'm just going to leave it solved for 1 over and then plug and chug. So we're going to put in a 2, we're going to put in our K, and then our T is 1800 seconds, and now you see those units cancel. And you see we've got liters per mole. That's going to match the units for inverse molarity here. And then we got 1 over our initial concentration, 0.050 molar. So we're talking about inverse molarity units there. So all of our units match, which is great. So we're going to say 1 over NOCl at time t. And we're going to run all that through our calculator and get our answer. So running that through our calculator, 2 times 0.020 times 1800. The inverse of the molarity is equal to essentially 92, looking 2 sig figs all around. So we'll leave it there, 92 liters per mole. But notice it has units of inverse molarity again. That's good because my molarity is inverse, so I just need to take the reciprocal. And so we're just going to take the reciprocal of our answer in the calculator, and we're going to get 0.01. We'll round to 1. And now that's moles per liter or molarity. And that's an answer that makes reasonable sense based on our initial concentration. So that we will be able to live with. All right. This is a table just summarizing our first and our second, which we have focused on in our videos up to this point. There's also 0. That doesn't come up a lot because remember 0 is independent of the concentration, so the rate is just equal to K. And so the integrated rate law would be A equals A sub 0 minus little a KT, or the half-life is the initial concentration divided by 2AK. Again, that doesn't happen a whole lot because it has to be independent of the concentration. Usually it's because there's an extremely large concentration of one of the reactants, and so changing it more at that point doesn't really impact anything. The two we're going to focus on a little bit more is the first and the second. So you can see the rate is equal to Ka, and then our first order integrated law, which we saw from the previous video, ln of A at time t equals ln of A at time 0 minus AKT. And then the half-life is the one we focused on. First order half-life is important, particularly as you move forward into nuclear chemistry, which we'll do later on in the term. But half-life is equal to natural log of 2 over AK. Again, the A is 1 for nuclear reactions. Second, rate is equal to Ka squared. And so we got 1 over A at time t equals AKT plus 1 over A0. And the second order half-life is 1 over AK concentration A0. So you have formulas for each. I emphasize the first order rate law because that half-life ends up being the most relevant to us. Not that you can't have half-lives of other things, but half-life comes up a lot with the radioactive things. And for graphical interpretations, 0 concentration versus time is a straight line, so you can actually plot these and determine the rate law or what the order is if you had graphical data. ln of A versus T is the straight line for first, and 1 over A versus T is half-life for second. Now notice for the 0 in the first, negative AK is the slope, but positive AK is the slope for the second. And then the intercept for the 0 is our initial concentration. For the first, it's the natural log of the initial concentration, and for the second, it's 1 over the initial concentration. And so using this handy dandy sort of table, you should be able to keep all of your formulas for this straight.